Okay, so then we need the lapel mic, right?
Yeah. And then I don't know if he has his own laptop. I don't know if hosts are encouraging people not to use their own laptop.
I don't think it's worked the last couple times if they have. Because they're still bringing the laptops.
Yeah.
You gotta send an email to Tim Johnson because he said he was supposed to have that thing this week and he never texted me. Whatever, let me know. Box and everything.
Oh, right.
Yeah. We're ready for the magic to happen, right?
Yeah. You know how to control this camera?
Yes.
Right here.
Yeah, so it has like pre,
Oh my God.
pre things,
Right.
but I don't know. See, that's projector screen, it's off.
Oh, I see.
So. How far we need to go. But this is that one I was telling you, look.
There's a front camera.
Right there. Weird, huh?
Yeah.
I never knew it. All this time, I never knew there was one. So here we go. You don't want it up, right? Because you want it.
In fact, I was just curious because I mean, the important thing is that we share the screen so that they can see the slides anyway.
Yeah.
They don't have to use the camera to see the slides.
Right.
So it's actually better just to have it on the person.
On the podium.
Yeah, so just lower it to the right, so you sort of see some of the screen and where the person would be standing.
Okay.
Yeah, just zoom out though. That's a good
question. Well, because it was on that
on the pre. Yeah, something like that.
Right, well, that's where it is right
Okay,
there. If you
all
want to
right.
play around with
Play
it.
around with it. Okay.
All right.
All right, thank you.
Yeah, no problem.
Good time. Grab some coffee.
No, I think.
Okay. Donuts?
No, yeah, donuts. I'll eat donuts. Plenty, I got plenty of donuts. And that's not about this. No trust. Decide, I wish I could mess it. This is
Yeah.
big.
Yeah, so we're on candid camera, the Zoom call has started. And you can, here's your microphone,
This.
is a
It's one
USB-C.
of those, no, it's one of those.
Okay, let me go find you one, that's okay.
You have that, and I do usually turn it, but I get it down.
Okay, so why don't you go, the microphone, is it on? Hello?
Just the, on top there.
Testing? Great.
I think the word they're testing 1, 2.
I'm spy. Dutch?
Yep.
Excellent, so I will go find you a little dongle, so all you have to do is,
Do you recognize it?
yeah,
I can,
Thunderbolts,
yeah, let's go on.
so you're gonna need to start your. Worst comes, well, okay, let me see if I can find a Thunderbolt.
He's gonna have to join the Zoom though, right?
He is,
I think so.
Oh, yeah.
yeah, will you join the Zoom? Do you know where the link is?
I can.
Okay, thanks,
Yeah, I
Rich.
can show him.
Do people show up on a Friday afternoon? Is,
Let's say we've had. The attendance has not been good at our colloquial lately, just 1 year, but. We've got EPS people and they tend to bring a larger crowd.
yeah, well, when we have turned Zoom off and told people,
We've had this
you gotta
debate.
show up.
We had this debate, yeah.
And if somebody says, we now send the Zoom link last minute, only to people who ask for it, which includes a number of retirees.
Right.
And everyone else is like, no, it's for real. Last week I pulled a fast one on people because I was hosting a speaker who had canceled last minute. The flight from, California, I'm like, I'm not telling anyone. It's gonna be on Zoom, I'm gonna project you on the screen, and everyone's gonna sit in their room. And they did, and then some people are like, why did you make us come? I'm like, we just need to get back.
That's right, that's
You
right.
two,
Yeah.
We need to share that.
Yeah.
And then. Not on Zoom, but you, so I will join that meeting. Okay, it still means I think I have to do.
There.
It may just be that, or it should be, I may be able to. I wonder if I have to type Princeton Zoom US. Because I'm at Princeton and then your number that might work. 0, 4, 0, to 8, unless it's somewhere.
Oh, no, that's another one. This is the one we're doing.
Oh,
Yeah. 927. 0969. 9696.
so that's, you probably have your own. Link. So in this case,
Because I think it's the equal that changes whatever plane it's with, so X is these over here, the Y is these here, and the V is actually closer. It's something that changes the price.
not the link now.
Yeah.
Copy the
Copy the link. Clipboard. Right.
Open the rail.
Oh, something.
Open the Google
Yeah.
Chrome. UNM, that's it.
Okay, UNM.zoom.us.
Yeah, because I guess that.
Yeah.
Don't use, and then the
Yeah.
J. that's
J,
the-
yes, we had trouble with the J. The pastor, I hope is Panda. Yeah, well, there it is. Panda, capital. Good. Then you should do.
Progress.
And my microphones.
Yeah, this is open for visual.
Where? Yep. And share my screen.
There is another.
Co-host.
I found a dongle. Let's hope this works.
You know, and I'm realizing that I now realize that we don't need it because of the Zoom,
Oh, nice.
but
Okay.
it all goes
Right,
down.
right.
Yeah.
That is the one.
That is what you, that's fine, that's fine.
And that's two HDMI. That's exactly what it is. Right.
Yeah,
So, but
that's
there's
what
no
you-
need to double plug in if I'm screen sharing.
Yeah,
Correct.
yes.
Hey, so do you say Slepian or Sleepian?
I say Slepian, but and I think that's correct.
Yeah, that's what I say.
That's, I think, a Hungarian name.
Is that right?
Yeah. And so.
So is the Landau in his paper that not Lev Landau?
That's a different one.
Lev
Yeah.
Landau.
Yes. And you know Dave Thompson, right?
I don't.
Dave Thompson is actually an astronomer now at Queen's University. But he came up with using these Slepian papers for multi-tape analysis in the 80s when he worked at Bell Labs.
Okay. So I was gonna say, is this common knowledge for astronomers? Do astronomers use
No,
Slepian bases?
not really.
But it should be.
Well, because Dave Thompson popularized it in Bell Labs and then primarily worked in geophysics, although now he's in astronomy. That sort of, although the son of Frank Press, Bill Press, who wrote numerical recipes,
Yeah.
knows about this thing. So the story of our using these spherical papers and then trying to bring them into cosmology.
Uh-huh.
When I talked to the astro chair, he's like, "Oh, of course we should have done that, and we forgot." And then he literally says, "I should have known because Bill Press was my advisor, and it's in numerical recipes, and and so the world is too small. All more reasons to just talk more to people." And it's the same in statistics. It's a bit of a niche area in statistics because Percival and Walden, who wrote this very good textbook. Percival is in statistics, but he's in Washington, and Walden is in Imperial College. And it's their multi-paper work is now mostly known in biometric art.
Interesting. So shape characterization.
Yeah, but on time series, you know.
Wow.
So, but people are using it, including a grad student who was, I'll show you my favorite picture while you're right. This is the best fitting space cat that fits in a spectral duck.
In a spattle.
In a spectral duck.
That's in a spectral duck. Oh,
Right.
that's cool.
And so it's the first three eigenfunctions of this Leppian concentration.
With
domain.
and those are spherical harmonics at the
No,
bottom?
this is actually Cartesian.
Oh, this is Cartesian.
But so if you're asking which space function is most limited in cat shape, while being most limited in duck shape, then this is three of the hundreds of solutions. And if you add them all up, this is you get in complete coverage of the domain.
Okay.
So that's the
spatial component.
So that's the Slepian Landau polymer basis, but our extensions for it.
Will you leave that cat and duck up while I introduce
I was gonna
you?
do a Thanksgiving, turducken.
You need to leave that up, not this one, yes, exactly.
So-
Leave that up while I
I
introduce
gave
you.
you the example, I should have been working on the grant, that's what I did in the summer, that was 2 solid weeks of work. And now,
The cat and the duck. All right, there you go.
now he's using it for solar magnetic patches, so he knows that I'm.
So just the helm, I best to wear it lower down.
Yeah.
So when you turn your head, it doesn't change the volume
Yeah.
so much. And it's just the top of the bottom, which is on right now.
You're not on a hot one.
Low down. I think the volume is up. Actually, the audience will come in. Right here.
You wanna.
Right there for a moment.
Yeah, it's pretty.
When I introduce.
But it's.
Happiness. Probably the main thing. You know, would be more.
Okay.
It's the last time that one such. So I'm gonna borrow your mic at some point when I introduce you. So we, what is, so. Power button. So is it? Yes. Got it. Oh, and if you need this is not the lightest in the world, but I'm gonna try to see.
Sometimes I know it. Oh, that's actually.
I'm glad you got it.
Yeah.
I've learned a lot, but just, hey, you know how to do that, it's where.
Really thoughtful.
Yeah, and so he's been working on this. Spanish. Did some work in. Well, using machine learning and testing how well we do this with a trained algorithm. So keep it.
And Brandon, Even a similar comment that he said he had some conversation with him, but not enough, but it was an inversion. Yeah, that we're talking.
Who keep?
Brandon and Pete.
Oh, I see.
Really what the university is saying is I can do my thinking at home and exchange of ideas and whatnot.
Wait, so do you have my intro is not very long, but this will so
This, even though I'm able to do a decade of my students, it's kind of running out later. Done something. I think that they got complete now. So it's like it never did that. It's like I don't just falls. This arbitrary.
yes, that's amazing.
But it all reduces to the.
Yeah, I still I look at your archive thing. It's really cool and mathematical, but I agree. All right, so when would you like us to start? Should we wait a few more minutes or get started? Okay. Okay. All right, welcome everybody. It's my pleasure to introduce today Professor Frederik Simons, who comes to us from Princeton, and he's a professor and associate chair of the geoscience department at Princeton. He's been working on things having to do with the seismic, mechanical, thermal, magnetic properties of planets and their moons and Earth in particular, Earth's lithosphere. He is very well known for devising really cool theoretical and computational inverse methods and statistical techniques. So to study really complex and heterogeneous data sets. And I wanted him to show this picture at the beginning because he's also really well known for using Slepian basis functions instead of spherical harmonics. So these are basis functions that are very handy when you're looking at incomplete data, let's say on a sphere. So if you're an astronomer looking at a particular part of the sky, pay attention because these basis functions, so these are, I guess, the first three eigenvalues of a Slepian basis, which is confined spatially to the outline of a cat and spectrally to the outline of that reflected duck or rotated duck. So this is a very highly specialized set of basis functions, but they turn out to be really, really cool for looking at data on a sphere. Among his many honors, he has been given the 2022 prize, the Kellis-Borak Prize in Mathematical Geophysics from the largest geoscience group, the global sort of IUGG, the International Union of Geology and Geophysics. And he's been applying these sorts of techniques to gravity time series, for example, from the NASA GRACE mission. But what we're going to hear about today is a completely different side of his work, driven by his love of taking things apart and tinkering. So a lot of instrumentation. He's going to tell us today about a system of technologically challenging, but floating hydrophones that, since their deployment, are changing our views of the interior of the planet and also our views of the ocean. So with that, welcome, Frederik.
Thank you, Osman. If you need a pet turned into a Slepian paper, hit me up. I can make anything for you. I'll do it turducken for Thanksgiving. So it's a completely different topic today, but one that is equally dear to my heart. And we really have been 20,000 leagues under the sea already with our seismic robot. So the story ends well here. The other title is really earthquakes, microseisms, and volcanoes. And I picked 3 different colors that I hope you can distinguish. And I'll be telling you about some very direct observations that we have been making using mobile arrays of microphones that sense ambient pressure variations underwater, so hydrophones. And I'm leaving the title slide up with the multiple names of the people who have been instrumental in helping me with a variety of things that I'll be reporting on, but I won't call them out individually now. But thank you all, collaborators, you are on the record. So, Geology 101. I don't think I need to cover it, but I'm going to do it anyway, right? We live on a planet that's chemically differentiated and physically deformed. And the record of that is in what you see at the surface and what you see in the subsurface as primarily compositional and thermal heterogeneity. It's not completely thermally homogeneous. It's definitely not compositionally homogeneous. And there's all sorts of chemical interesting things like phase changes that change material properties. And so those changing physical properties of the materials building up the inside of our Earth, both solid and liquid, affect the propagation velocity of seismic waves. That's seismology. They cause anomalies in the gravitational field, including time-dependent ones. They are manifest as surface topography. So lumping all of geology, geophysics into these 3 words here, you look at the surface, you study the Earth's gravity, and you look at seismic data to image the interior, you're going to get a good picture of what's going on. So that applies to other planets. As you know, Mars is the latest planet that we have instrumented with 1 seismometer, and an amazing amount of information has already come out of that. The Moon we have instrumented with seismometers. For both Moon and Mars, we have done gravity, and clearly we've done topography. So just to sketch the theme here, seismic velocity, that's not just elastic wave propagation, that's not just isotropy, that also includes attenuation, anelasticity, anisotropic properties. Gravitational anomalies, that's not just here's a density, that's what the Newton effect is, but it's also the dynamic effects of how it affects the deformation in the interior of the planet. So those are static, dynamic, and time-dependent effects, including the effects of the loss of ice sheets that we now experience, which is directly observable from time variable gravity. And then surface topography, that's where all the cool interactions are, including with the atmosphere and the oceans. And so when we look at their interactions, their correlations at a variety of scales between all of these fields in a giant matrix of observable points of study, this is, to me, summing up what solid Earth geophysics at the planetary scale really is, and has become over the last couple of decades. Anyway, topography is the elevation above a gravitational equipotential, and bathymetry is the depth of the oceans as the inverse of that. And you all don't need a reminder that that's what it looks like, but you would all probably still be wondering and looking in awe at some of the features. How did that particular thing form? What even made the continents? How long have they been there? How stable are they? What are those features that you can point out in the ocean floor? They all have reasons, they all have dynamical reasons, they all have interior reasons, and they all have reasons for us to study them. Gravity, this is a picture of the free air gravitational anomaly. This is when you take into account the observational height differences, and so think about it as at satellite altitude, and the gravitational acceleration is not constant, and of course at every point on the Earth, it's a value, and ultimately all of that is reflective of the entire density distribution on the interior of the Earth and how it changes. It's not a gravity talk now, but if you watch it change, it'd be amazing. You'd see the seasons, you see the hydrological cycle, you see the leaves coming onto trees in large domains, you see irrigation, you see droughts, you see earthquakes, you see ice melting, you see all sorts of things. So that's gravity studies have become a very dynamic area of study. And then seismology, that's earthquakes and how their waves propagate through the Earth. And this is just a snapshot here. Well, rather, it's 30 years of earthquakes as detectable globally. Any
high quality seismometer put almost anywhere on Earth will record earthquakes of a magnitude 5.5 and above. And if you just put like a here or not everywhere that happens, you have about 2 of those a day. So you don't need a reminder that the Earth is an active and dynamic planet. But of course, one of the things that you see is that the sources of that energy are not randomly distributed across the globe, but they delineate plate boundaries. They have the rare interplate earthquake. They have ridges. They show basically the story of plate tectonic in its outlines. Anyway, ultimately, it's chemistry, right? How hot is it? What is it made of? And that turns to physics, as in, densities, wave speeds, and that then tends to geophysics the moment we observe it and interpret it. So over the years, we have put many high-quality seismometers in many places, including some of the people sitting in this very audience. And earthquakes come and go. And we use the principles historically of optics to derive first order properties of what these rays are doing. The very fact that they bend and come up tells us the wave speed generally increase with depth. The fact that they sometimes bounce back tells us about the first order phase transitions in the system, where certain mineral assemblages turn into other atomic arrangements. That gives us very sharp reflections. The fact that something goes from a solid silicate aggregate, which we call rock, to a liquid made of predominantly iron is immediately observable by downloading a few data from our national data centers, and you're seeing the shear waves disappear. So the first order structure is beautiful in a way and nice pedagogically, and it is very well known. Fast forward to the sort of state of the art that we're doing now in seismology. No longer do we trace rays and geometric optics, but now we have built, and I'll tell you about how we do it, entire Earth models for the interior of the Earth, which include its topography, its elastic and anelastic interior, its sharp interfaces, its smooth perturbed domains of areas of heterogeneity. The rotation of the Earth is manifest in the seismology that we're able to record. The self-gravitation of the Earth is manifest in the seismology that we record at very, very large frequencies. And all of the things, all the essential things of global planetary wave propagation, including all the interfaces and the fluid solid and ultimately oceanic and atmospheric coupling, is now sort of state of the art in a program that my colleague Jeroen Trump has been leading over the last few decades, and that's called the Spectral Element SpecFEM 3D Globe. And so if you go to the Shake movie website and you're interested in your local but globally observable earthquake, there will be a simulation lying around there for you. And I'm just showing you with a couple of snapshots of to send to you the idea that, of course, earthquake waves propagate globally, that there's a lot of structure in that wave, that you're immediately seeing fast and slow and spread and scatter and coda and all surface waves and there's a whole wave field, reflections, diffractions, transmissions, and all of that is amenable to numerical modeling. And so ultimately, when we do seismology, we are able to take an observed record and compare it to a prediction, a numerical prediction of, and within a 3D Earth model that already is very good. Here I'm showing you not the best, just a random, relatively low frequency seismogram to show you that point that in an Earth model that we already have, for an earthquake that we already know about, the wave train at some station that we pick will be looking slightly different than the observations, and the information that we mine from the seismogram is arrival time differences, amplitude differences, dispersive differences of the different types of waves that bounce up and around in our planet. Slightly different from the stuff that you may have seen going on Mars, because there's only one seismometer, so there's a sort of different set of seismology that's going on there. But that's the difference, right? Slight phase adjustment, slight amplitude adjustment, slight timing adjustment, and that's how we adjust the interior Earth models in order to match ultimately whatever data that we record. So the global science of seismic tomography is like X-ray tomography in the sense that we have a source and we have a receiver and there is an effect along the path. It's much more interesting, I think, in seismology than in medical tomography because it's not intensity, it's actual wave motion. And of course, as you know, in a hospital setting, you have as many sources and detectors as you want and you can place them at will. You have to be careful to not set your patient on fire. So that's definitely a bit of a limitation, but that's unlike in the Earth where we cannot choose where earthquakes happen, although we cause them all the time, but not typically large ones. And we can put multiple stations in many places, but that's what I'll be talking about. When we don't need to conquer the oceans, new solutions are called for. Tomography in 3 slides, there will be data, there'll be unknowns. If you think of it as a gridded model, not the only representation, it's all about trying to fit where the waves are delayed or sped up, where they're diffracted, reflected, and so on, compared to an Earth model, and then collecting multiple data and multiple unknowns, you have a chance at inverting for the velocities and other parameters, blast parameters, density parameters, and elasticity on the inside of the Earth. So the Earth in 3 snapshots for people who may not always look at it. There's the Earth lithosphere, which Musumi and others studied. This is from when we were together not in Australia, in grad school. I was working in Australia, and blues are faster than average wave speed propagation. Reds are slow. Typically, blues indicate denser material, typically colder material, typically older material. Reds typically indicate hotter material, younger material, buoyant material. And so the source of, trying to find what the lithospheric keel was, what happened to the old places in which it wasn't as thick as predicted. This is some of those stories of, might it have been as thick and actually been dynamically lost? Motivate this sort of continental studies of what seismology can tell us about the structural and evolution of a variety of continents. This is the stable bits of the Earth. That's the literally sometimes translated as the scum of the Earth, is the buoyant granitoid rocks that form the Earth's continents, which are old and stable. Here are the things that go down in the Earth. And so there is a dynamic and a fluid mechanics problem is for some reason, when the crusts get formed and then they cool and then they thicken and they become negatively buoyant and then tend to sink down in sheets, and those we call subduction zones. And here, this was my office mate at the time running through a variety of subduction zones. And here you try to track the blues, and the blues are areas of active downwelling in sheet-like zones. And so that, as you can imagine, is a source of large earthquakes and a source of much tectonics and reconstructions through these variety of models. And then finally, there's the stuff that comes up, right? Mass is conserved, and so the stuff that goes down in sheet-like downwellings tends to come up in columnar upwellings called mantle plumes, like in atmospheric convection. Here is a planform at a particular depth in the Earth, about 450 kilometers down. And the reds, again, are areas of slower than average wave propagation, which tends to indicate hotter than average material, which tends to be buoyant. And so by inference, and this is why the author here, Ibru Bozda from Colorado School of Mines, labeled particular areas of volcanic interest. Actually, we just did talk about that in the meeting, but I didn't know it was on there, Raton. Areas where if you know at the surface, there's volcanic activity, there's magmatic activity, there's things that come up because buoyant material tends to rise. We are trying to look at where that origin is, where the source is, how the precise geometry and plumbing of that convective global circulation system works. And so the hints here are, the various areas that are ultimately underneath some of those active areas of volcanic upwelling already have their source signature deep down into the earth as part of a global convective system, but more blob-like, more columnar, not sheet-like. So if I then sum up, these are all the successes, right? We can do numerical wave propagation beautifully. We've done hundreds of years of seismology. We know how to record seismic activity. We can model all sorts of processes of interest. Of course, what we cannot do, despite all the research to date, is put earthquakes where we want. So this was just a handful of days now, almost 20 years ago, when I was looking for earthquakes, and this is what happened then. Okay, so that's what you get. And if we look at the high quality stations on Earth, there are thousands of them, but the ones that have really long-lived data centers and so on, and we just put a little wide circle around them, then of course you're seeing that the continents are relatively well covered, but the oceans are a blank spot. And here's another more up-to-date map of where the global seismographic network is and which agencies they belong to. And it's far from uniform, but yet it's high quality and very good. And some of this data is going back for a very long time. So in the oceans, though, not much, and they're big. So when I was a postdoc then, I was working with Hunga-Tonga, and he had just spent a sabbatical at Scripps, and he's like, well, look at the oceanographers. They're building an array for the ocean to map ocean currents and global distributions, conductivity, temperature, depth, to map the world's climate and its influence on the oceans. And 20 years later, thousands of those sensors return data every 10 days, entire columnar profiles that they make with hydrographic, oceanographic measurements, including where is the instrument, which itself is a current measurement. And so Hunga-Tonga is like, we should be able to divert one of those things and to do some seismology with. Well, let's try that. And so that's what we asked. Argo is the name of that program, and we thought let's build something resembling that. Even one would be good, and we'll see where we go. So we decided we could try it. And then he came up with the acronym MERMAID, Mobile Earthquake Recording in Marine Areas by Independent Divers. And those of you who thought I was going to talk about actual mermaids can leave now, if that's because that's really what the mermaids are. Okay. And so here's the principle, right? We send instrument down to a depth where it's quiet and unbothered by anything, and it just drifts, and it's recording its depth and its temperature and not its position, because it doesn't have a GPS down there, and it will just have an acoustic recorder on. And then if it finds something, and that was much of my research early on, how to determine when something was worth spending the energy to resurface, report, and then come back. That's the principle. That's the cycle. So if it finds something, it's going to report it and then return on its mission. And well, what all can it find? What is the ocean making in terms of noise? Right. That's a bit of an issue. So I'm just going to discount the sound of icebergs moving and cracking, which I know some of you are studying. I'm going to discount whales and other biological activity, interesting, but not in my frequency range. I'm going to discount ships and submarines, if anyone's asking. And you're going to focus on the things that are solid earth generated, right? So earthquakes, nowhere near, not in the ocean. This is, way out. This could be Japan, the other end of the world. But in the solid, sending those body waves, the P and the S, the shear and compressional wave variety, surface waves of the Rayleigh and Love variety, if those terms mean anything to you, waves that interact with the bathymetry close to the water or in the water column or close to parts of the water column that then send acoustic waves in the form of T waves. And all of these things, small as they are, perturb the ocean significantly enough to result in an acoustic wave of the ocean that can be picked up in principle by this instrument called MERMAID. So initially we built this array and we thought we're going to get the P wave because that's already amazing. The first arriving compressional motion from which we've built entire stories of the Earth's interior through tomography. And later on, we realized also that we're getting plenty of later arriving phases and all sorts of complexity that I'm going to talk about. So the instrument is in the water. The earthquakes are worldwide. And this is why we're having trouble getting funding, is because nobody understands that you can work in the ocean and not study the ocean. Okay, so it's an oceanic data collection for the solid Earth, although we've been updating that picture. So sometimes I make this the sob story of the development because MERMAID 1 was one instrument that we made. We diverted one of those solo float, as they were called. We put a little hydrophone on top and a nice flag, and we ran it with different sets of experiments. And I recorded precisely one earthquake. And for a good 5 years or so, I went around with this very seismogram, which showed that it could be done because there had been one earthquake recorded by a completely freely floating instrument. 5.6 of a global earthquake, 46 degrees across the surface of the Earth, so 5,000 kilometers away, and relatively whatever. This is what it is. It's a little bit filtered, and so it was expected to arrive at 0 because, of course, that earthquake was heard around the world, and here's that first waveform that we ever did. So, second generation, different manufacturer, larger vessel, different color, more batteries, everything updated, and an autonomous reporting built in that the first one didn't have. That was MERMAID of the second generation. And with that, we did go around the world, even though only about 14 of them were built. We took them to the Mediterranean, we took them to Indian Ocean, we took them to various places. And whether you're a seismologist or not, you're recognizing that these are all unfiltered records, just time domain stuff showing you P waves, BKP, these are all various waves, some of them going through the Earth's core, some of them from the crust, some of them nearby, some of them far, but we've collected a lot of different waves from different earthquakes, including from earthquake swarms that were not heard anywhere else. So that was the sort of thing, you're in the Indian Ocean, and suddenly there's 243 earthquakes from a nearby plate boundary that were small enough, but close enough that we could hear them, but that no other seismometer on land did hear them. And so that gives you an entirely new set of information for the global seismic budget, the local tectonics in this area, because we hear things that nobody ever did hear. And that's that column here that was literally 250 earthquakes that just showed up here. These we deprioritize for the simple reason that if an earthquake is nearby, it doesn't tell us very much about the interior of the Earth. But if an earthquake is far away, it travels through the Earth, and then we can do the tomography and the modeling and everything. But so this is the sort of junk phases, and these are the ones that show you that we can do global things. So that sort of became an increasing success, and we tried to do a first tomographic experiment to image the structure beneath the Galapagos Islands, which is a volcanic set of islands that you all know from Darwin. And I'm just going to go through 2 slides to show you that we did it and that it wasn't ultimately the best of successes because we only had 11 of the second generation mermaids. They only lived about 2 years, and they didn't go really all around and making a nice aperture array the way we were hoping for, which would have been nice to image a purportedly columnar upwelling underneath. Here are all the surfacings where earthquakes had been recorded. And so you see we're kind of far from a nice coverage, but nevertheless, we were able to do a global inversion for this regional piece of it and image the highs and the lows of the wave speeds. And in a different talk, I would be a little bit more going in depth into what we think we have seen. I mean, we think we do see a part of a plume system, but there is a lot of complexity and it's not all quite clear. And so my question mark here is to say, well, look, it shows you that we had all the earthquakes, but not enough. And we could do the modeling, the timing was impeccable, the locations that we interpolate, all of that is good, but it's far from a complete picture. And that led us to say, well, we really need to move to yet another generation that can be alive in the ocean longer, and that we can have more of, such that we really realize this vision of a grand oceanic array with which we can tackle any sort of experiments on the inside of the Earth. If you had been wondering, so 0 to this is this slice here, right? So this is a piece through the mantle, right, down to the core mantle boundary. So the reds and the blues again are the regions of faster and slower wave speed propagation. But because I find these images to this day, you know, a little bit underwhelming, I'm going to focus on the fact that we use this as a motivation to do better in the instrument design. There was a slight offshoot that was a sort of a combination of a sonobuoy and a mermaid, which I called Sun-O-Mermaid, which had 2 generations. And all I want to show is that they generated amazing pictures. And despite me naming the 2 of them with the first name of the NSF program managers, it really wasn't a ticket to a lot of funding. And so that is a development branch that has now ended. So we no longer have Sun-O-Mermaid 1 and 2, but I do wish to acknowledge their contribution. So that's Robin Reichland, if you're asking, that it didn't really work. Anyway, Mermaid 3, that's the one that we're really now having a lot of good success with. So what is it that the others didn't? This is the nude version, if you will, without the cladding. Iridium for communication, GPS for timing and for location in a joint antenna. Here's a hydrophone, just an underwater microphone. An internal oil reservoir that pumps oil around, hydraulic fluid, to be able to be neutrally buoyant between 0 and about 2 kilometers depth, about half the average ocean depth. We're building a new version that will go to 4,000, and there will be other versions that will do the whole ocean depth, but it doesn't really matter. We're very happy at 1,500 meters depth. We're hearing all sorts of things. A glass sphere that you can buy, proprietary electronic boards, which include the algorithms that we developed to give this thing the autonomy to decide when to spend its energy to report. Importantly, for those of you interested in the ocean, open ports for more instruments. You want to measure something, we might be able to hook you up, quite literally. And then the buoyancy device. So that's Mermaid 3. And we got together a consortium of people that we called EarthScope-Oceans, which collected seismologists and others interested in ocean acoustics, but for solidar seismology, and involved people from Japan and China and France and South Korea and a variety of others. And we are in the current phase where we decided that we were going to image the mantle plume region underneath French Polynesia. And to date here, we're collecting data. So to get an idea of the form factor, they are light. They can be simply deployed. Any boat can do it. It takes 5 minutes to turn it on. So deployment is, the ease of deployment is a real issue because the ship is very expensive. And so if you do an ocean cruise with some proper equipment to go sample the ocean floor, it'll cost you an arm and a leg, whereas this one you can mail around and anybody can deploy it. So that's that was one of our first or second deployments. So I just want to give you some fun photos. So if you are ever out in the ocean and you see that, it's one of our instruments. It spends about 15 to 30 minutes on the surface, looking and locking to a satellite for communication, sending us some data and taking some messages for its next descent, which is usually keep going because we don't interact normally with it, and then it'll be gone again. And so far, so the oldest ones are now 4.5, almost 4 years old. So they have been doing very, very well. Really, I'm very pleased. It's a French engineering firm that makes it, called Océan. Anyway, so that's the fun photos. Where are we now? It is not actually a screenshot from last night. I meant to do that, but if you go to earthscopeoceans.org, or you get our handy iOS app called Adopt a Float, you will see where our instruments are and have been, and you'll find out a little bit of information. So ultimately, about 50 instruments went into French Polynesia that I'm going to talk about. Since then, we put some instruments in the Mediterranean to do something else that I'll talk about briefly. We also have some things in the South China Sea, or depending who you ask, the Philippines. And here's the source of the 20,000 leagues, right? So over time, we have collected hundreds, thousands of surfacings. This is from a paper published this year, so that was the first 18 months only, and every little worm here is a little trajectory in time. You can see the array we put out in Polynesia was basically a straight shot here from New Caledonia, Wallis and Futuna out to Tahiti, then a circle around it, and now it's almost completely dispersed. You don't see that original signature in there. We're building a database of data, thousands of events now, with which we are feeding the tomographic inverse model that is nowhere near ready because the data are still coming in, and I will not talk about the unfinished results. A growing catalog of earthquakes of all magnitude. This picture is the published version. We have now tripled, if not more, the number of earthquakes resolved in the earth. So for the investment, this is a massive return. We have returned thousands and thousands of high quality seismograms that are all useful for that type of seismology we wanted to do, imaging the interior of the earth. So a little bit more about why we're precisely there. You know, the earth is made out of plates. They're involved in tectonics, and together that's called plate tectonics. But things like Hawaii don't fit into the canonical picture of a plate. It's an additional feature of one of those deep mantle upwellings that punctures a plate, and because there is a plate that moves, we see the Hawaiian emperor chain around it, and so, but this is part of that global circulation system of the earth. That's Hawaii, just so you all know it. French Polynesia, you know, we think it's the same. We think, if you look at a not to scale canonical textbook, we think there is some feeding material, or we think there is some volcanic material that comes out, and French Polynesia has thousands of volcanoes, and we're trying to figure out precisely what that system is. You can see in this, 101 textbook, there's no features here of the mantle, and we're like literally just trying to piece it together. So back to the intro here, temperature, what is it made of? And the wave speeds, remember, that's what we're measuring. And what do we need? Earthquakes, point sources of energy, seismometers, now we have MERMAIDs. We need a reference model, something, constructed from prior work, bad or good, we'll update it. Then we need a lot of forward computation to make all those seismograms fit the observations, and then we invert, iterate, however we do it. And there's a lot to say about it, and that's how we make those three-dimensional models by tomography. So, reminder of this region, this is somebody else's model, not with our data, so that's sort of a state of the art in this area. The central region, centered around French Polynesia, or let's call it Polynesia here, is a region where we think there are broad upwellings. And we'd like to get some detail. You open a journal and people publish. This is, I don't know if I like the picture. It's intricate and I'm not sure how to describe it. This is a hull of isosurface, and so the geodynamics and geophysics are trying to figure out where material goes, right? And so this is in a different area just to give you a state of the art of what people are interested in piecing together. The complexity that is to be expected when one studies a large-scale circulation system made of hot rock that moves around. Our problem, as you've now heard many times, never enough earthquakes and definitely not enough seismometers, but we've just sort of made a big dent in it by putting these MERMAIDs out there. And then the seismological angle is that the reason that the slow wave speeds are actually fuzzy is itself a diffraction effect, because the waves tend to defocus away from it. And so it's kind of harder intrinsically to measure the red stuff that upwells rather than the blue stuff that goes down. That's why we're doing it. This is a view of the island of Moria from the island of Tahiti. This is what in the late 90s we thought the plumbing system would be like, some large blob, interpreted again as, a large blob. And other models, I'm just trying to give the state of the art here, have imaged a variety of pieces of evidence that here is Tahiti, here's the Marquesas Islands, here's American Samoa, that really do show you that there's definitely some upwellings whose geometry, evolution, structure, we're really trying to piece together much better. So that concludes theme one is earthquakes allow us to image the interior of the earth. And if you can measure them in new places, it's like you're shining a flashlight on a piece of the mantle with much more detail than you'll ever have ever had. And that's ongoing. Thousands of earthquakes reported, and the study goes on. I didn't say it, but it's implied that the MERMAID instrument is not recovered. You throw it overboard, it's autonomous, it doesn't steer, it passively drifts with the ocean current, it reports the data. We're not going to get it back. It'll float up and it'll be washing up and it'll be fished up and so on. But it's not intended to be recovered because that's unimaginably costly. However, we did recover one of them because in the course of several deployments with several different ships, we managed to steer close to one of them and after a year pick it out. And so that's how we had access to the entire almost 1 year buffer here from 13 September 2018 to about a year later. And it had done this trajectory, in this vast ocean that's still only about that big, right? And we had already had the earthquakes reported from it. Now we look for the earthquakes that we knew there were that it hadn't reported because they were uninteresting to the algorithm, or they were too small to really trigger certain parameters, or it might have just missed it. And then we look for all the other signals that were there to account for everything. And just to drive that point home, if we look at all the time domain seismogram that comes out of MERMAID, normally we'd be dealing with 5 minutes of data because that's the little snippet that's enough to do the first arriving waveform tomography. But if you keep listening, you're seeing all sorts of things. This is time domain, this is the spectrogram, and frequency goes up, and this is time. And of course, you're seeing here this red band of noise that is always in the ocean. The waves, the P wave here, that's the clearest one, that's the first arriving compressional conversion here, that shows up right there. And it's immediately clear from it. So the algorithm picks it out very clearly. You're also seeing the S waves. You're seeing a hint of the surface waves. You're seeing T phases from other earthquakes, which are just purely hydroacoustic phase. But let's just take a look at that wide band between 0.1 and 1 hertz that is just always going on. That's the noise of the ocean, okay? And that gave us an unprecedented opportunity to just make a day by day, hour by hour, week by week, month by month calendar of what the spectral density evolution was of that noise that we were seeing. So that red band is the peak here between 0 and 1, 0.1 and 1. And so all of them from your perspective look the same. This is 20 hertz. We sample at 40 hertz. It reaches to 20. The filter actually filters it. So really it's 10 hertz in this example. Then there is a flat plateau, then there is that humongous hump, and then there is a trail off where our instrument actually does lose sensitivity. But so here, we're going to look at what the day-to-day, month-by-month variations of that noise are. So in other words, we're asking, what is the ocean doing to make these things interestingly varying? So what's going on at the ocean surface? Wind and waves. So there is a model out there, WaveWatch, that uses all sorts of non-MERMAID observations to piece together retroactively what the state of the ocean was. And here is just a snapshot of a couple of hours. These are actually forecasts, but it's in the past, so it's hindcast. And that's storm systems propagating and making swell, making waves and driving the ocean to also have noise. And last year was a timely year for that because this is Klaus Hasselmann, who got a Nobel Prize for something completely unrelated, but he did a lot of work in oceanography in the 80s, I think, over in San Diego. And he figured out the famous mechanism now by which large-scale interacting ocean waves that interact with each other and with the continental boundaries would set up whole ocean oscillation systems which have acoustic modes that drive the ocean floor, and that is seismically recordable. So that's the Hasselmann mechanism of secondary microseismic noise generation. And I put his picture in because I was looking for it when he got the prize for something unrelated. And so here is the Hasselmann mechanism in a nutshell, and it's two of the same plots, 2 different weeks. And so MERMAID is in red, and this is one of those spectral densities. And wave watch is the ocean model, and that's in the other color, which I think is blue. And Hasselmann's mechanism says that in this frequency range, if you multiply the frequency by 2, then you have the seismic response, the acoustic response of the oceanic driver due to the nonlinear interaction of surface gravity waves. And so what I want you to see is that if you shift this peak on a frequency times 2, that it is matched in shape and in amplitude. And I'm showing that even better here by looking through the whole year. So this is the work of my student Pete Pratankorn, who plots on this axis the wave watch ocean wave frequency, and here the MERMAID's recorded acoustic frequency. And Hasselmann's mechanism says that it should be coherent on a 2-to-1 line, which is the dashed line, and coherent here means red. And so we're saying, well, look, yeah, we are observing the generation of this microseismic noise from the interaction of nonlinear interaction of ocean waves, driving the pressure at the seafloor to like thump the ocean floor and generate seismic noise, but we're seeing it in situ, and it is very coherent. You pick out C here, that's the best one. This is through an entire year. The ups and downs of what the ocean is doing are really just measured in detail by MERMAID. So what that means is that MERMAID is now an environmental sensor that is sensitive to what the ocean is doing, and that opens up all sorts of new avenues for it. So that's not earthquakes anymore. That's not what we call microseismic noise. That's what happens in between the earthquakes. And MERMAID observing the secondary microseismic generation mechanism in situ before it's even hit the ocean floor, which for us is a nice thing, which we never thought we would be able to do. So MERMAID is an environmental ocean sensor. So meanwhile, on the ocean floor, okay, we talked about the ocean in the column and the earthquakes recorded and what we do for the interior of the earth. Then what the ocean is doing to generate the noise that we're also hearing. A side story developed where we were wondering, well, this secondary microseismic noise that we understood since the 50s, 60s, 80s, and the work of Hasselmann, that is good at generating surface wave noise of the Rayleigh wave variety, which means this is essentially saying the up and down motion of the ocean waves translates into roughly up and down motion of surface waves propagating along the surface of the ocean. That is well understood, and we've now observed it even better and in more places right in the middle of the water column where it had not been observed, thanks to this new instrumentation. But there is a lot of noise on the transverse components of any seismometer of the love wave variety. And love waves are the transversely polarized surface elastic waves that are running across our Earth and that are apparently also stimulated by some mechanism. But even Hasselmann couldn't figure this out because I mean, he didn't bother, I think he would have, but the real question is, how does the heave of the oceans produce sideways sway of the Earth? That doesn't really compute very well. And so well, that's the question that that's our side question here. How is the ocean able to generate these particular love waves? And the two theories were, it's probably bathymetric variations because, the up and down motion gets force split at bathymetric inclines, and that will push the Earth sideways, if I use simple language here. But there was a side problem here that we had to identify, and that is how to actually identify the transverse component of motion of something that isn't a particular event, but actually just the noise that is diffused and generated from everywhere. So here in a couple of slides, I'm going to show you the work of Lucia Gualtieri, who was a postdoc with us at Princeton at the time, and so she combined the wave watch forcing with one of those numerical Earth models, including topography and including the seismic wave speed variations that we're also basically trying to image using tomography, and tried to put the wave watch driving ocean waves, the SpecFEM numerical modeling, and then try to tease out from global high quality seismographic stations what proportion of transmotion there could be explained by what, and I'll tell you what the result is. And so that literally did solve a 100-year-old problem in seismology, is that nobody had actually really been able to put their finger on the precise mechanism of love wave, transversely polarized waves of the secondary microseism. So here's 3 slides of Gualtieri's Lucia's work where she's like, look, if it's a regular earthquake, like a seismogram that I can show you, then it turns out that if you plot acceleration to rotation rate, that there is a relation between them. And if you look for correlation, then you can identify in areas of high correlation that is wave motion of a particular polarization. I don't have to belabor the details to show you that if you have multiple components, that you can work out relations that are diagnostic. So again, for an earthquake, this is easy. Then you can see that in this period, in the period of time, there is in this particular azimuth where we expect the earthquake to come from, a clearly identifiable component that is transverse to the direction of the wave's motion. So this is an earthquake seismogram, and you can tell that this is where the love wave is. Anywhere else, there isn't a clear relation, and so that's basically nothing. But what do you do without any earthquake? Well, it turns out you just do the same thing and you try all sorts of azimuths. So here is the example of finding a love wave without an earthquake when you really can't find anything. So here there is no maximum to this correlation. We try everything. But if and when that happens, we have detected transverse energy of the noise field, and we have detected where it came from. And that is shown here, that over time, for just a random noise sequence, or to the eye random noise sequence, we can sort of beamform the azimuth of where the transverse energy is really coming. And so the distribution of here of where these maximum crosses are distributed tells us, okay, so that's a direction from which we have this transfer motion. So she did that for all of those high quality stations and then tried to find the mechanism. And I'm cutting the story from ABC2D, where it turns out the result is, well, here is why we are able to generate transverse love wave motion from up and down ocean wave motion. It's because the Earth is not only interesting in its topographic variations, which does produce some force splitting, but it's those internal variations. It's, in other words, a 3D Earth model that redistributes the energy that, you know, is driven randomly through the ocean, and so through ergodic interactions ultimately fills the state in the right proportions that we get energy distributions across the 3 components. And so she showed that with a detailed analysis of, you know, all those high quality stations, a detailed Earth model with the realistic 3D variations, and then all the detailed numerical model that showed that that really was going on. So here's a couple of these stations here. You're, you know, looking at one of them, you do this beam forming, and then you say, well, where is that transverse energy coming from? And you see here that they point to this area here, and this area here is just for that week where the storm activity was. So now again, of course, the land-based seismometers are environmental sensors because they're hearing the ocean, and not just in the predictable Rayleigh waves that we already knew, but also in that other kind of waves, the transversely polarized love waves. And if you just, you know, point the directions back to the source, then that's the sort of resolution. This is not, you know, perfect, but we're able to explain the mechanism by which it happens, and we're able to use it for the purposes of pointing to where storm systems are coming from. So of course, this is all land-based seismology. Technically, it's nothing to do with MERMAID, but because, you know, we were in the I think it fits in the story that as we're seeing Rayleigh wave microseismic noise generation, we also should ask about the love wave, and we were asking at the same time. We elucidated the whole different problem at the same time. Anyway, so that was microseism, and I have just a little bit to wrap up here. Oceanic pressures and noise sources, they do generate love waves in the earth. If you didn't know that, well, it was a problem for 100 years. And it's primarily by the interaction of the wave field generated by the ocean waves through the three-dimensional scattering of heterogeneity within the earth, much less so from the bathymetric interactions, although they count too. And then the last thing here is, well, now we had all these records, and Pete looked at all the noise, we looked at all the earthquakes, we found a whole bunch of other ones, we looked at all the ships that went passing by, and then there were just a lot of hours where there was noise that we had no cause for, no identifiable event. And so just some random time series and spectrograms, don't worry about the details, but the stuff that you see, there's something going on that you don't know what it is. Different scale. And then, of course, Hunga-Tonga happened, which if you haven't heard, it's time to hear about it because it was heard around the world, right? This is like the January 6th of the ocean, except it was January 15th. The bomb that went off, and every barometer on land heard it twice, if not more times, because the wave went this way, the wave went back around the earth, and then back again. And is that my cue to stop?
It's Hunga-Tonga again.
It's Hunga-Tonga again. Yeah, I think it does work now.
Okay, it's fine. I don't know what that was, but
You're an engineer now.
I am now.
Anyway, so here we are with 50 instruments recording acoustics in the ocean, but we were just prioritizing earthquakes, and we had recorded all these things, but we are able to dial into the instrument, and it maintains a 1-year buffer. So we started requesting data, and it takes a while to get the request because normally it sends 5 minutes of data every week or so, and here we are asking for hours upon hours. And this is my postdoc Joel Simon, who's writing that paper now, where it turns out that many of our instruments okay.
I think
I think the battery is literally dying. So we heard it on all these different mermaids. And we're now collecting a really unprecedented data set of noise that didn't contain any earthquake, but that is going to help us figure out what really happened in the source mechanism of that volcano. Was it one? Was it two? Was it a vertical pounding? Was it an explosion? Was it a spherical thing? Was it isotropic? Was it not? No, just I know the time is up, so I'll just show you that we have and are studying it. So that would have been really, I'm not going to go through the little bit of detail I was holding, and it'll come, but we hear a lot of random volcanic activity. Hunga-Tonga wasn't random. Everyone's interested because we were right in the area, and this is a source of an ongoing project here where we're actually done with the data request because we've reached the 1-year mark. But we're trying to work out why the detailed differences in recordability of the event came about, what it tells us about the source or the mechanism or the interactions again with the bathymetry. That's it. So land-based arrays need oceanic counterparts. Floating mermaids are doing the job. We can now do the interior of the Earth imaging that we've done for 40 years in more detail in more places. We have a program and a consortium. We're assembling a tomographic quality database. We've proven that it is of the quality, but we haven't done the tomography yet. That's ongoing work. In the meantime, we're also getting a lot of noise. That noise is interesting by itself. It tells us something about the ocean. The ocean then drives again the seismic noise, which became the side story of trying to explain microseismic noise of the type that really hadn't been properly explained, which we did numerically and by confrontation with data. And then there is that, one-off, Hunga-Tonga, we are the only array. There are like 3 other hydroacoustic stations from the International Nuclear Monitoring System that have records. And of course, it was heard around the world in barometry and in seismometry. But here we are relatively close to that source with 22 or so of instruments that were not busy doing something else. We're not at the surface, we're not, and now we're working out what the differences are in propagation, source, and path effects to see what we can learn about that particular event. And then we'll move on to something else. Thank you for your attention.
Thank you, Frederik. And yeah, so if people have questions, raise your hand and I'll watch the Zoom as well. Yeah, question.
Just so that
You might have to speak way up.
or I can repeat your question to the Zoom.
Well, I have 2 questions. One of them is how much it costs one of these instruments? And the second question is, like, do you have any plans to deploy this kind of instrument, for example, in lakes, to understand like lakes microseismic, because they also generate their own kind of like noise type?
Yes, I even thought about putting them in a borehole, the Great Lakes, the Mediterranean is a bit of a lake, so that we are interested in all sorts of things, and yes to the deploying anywhere, but we have no immediate plans on that. And that's it. How much they cost to buy one? A regular off-the-shelf one is about $35,000, which is about half the cost of an ocean bottom instrument, and it costs almost nothing to deploy, and the data are immediately near real-time available. So I deployed 11 of them, and I was looking at my data the same day, because they do a trial run, and then like 3 weeks out, you're still on the ship and you're already catching earthquakes from the instruments. And so the risk is completely different order of magnitude with conventional ocean bottom techniques, where you buy an expensive instrument, put it down, and leave it for a year or 2, and then you send an expensive ship to it to return data, which sometimes doesn't return anything at all, because you have to pick up the instrument. Some of them don't ever return anything. So in terms of, earthquakes for the buck, hydroacoustics, you've seen the records and you've seen a little bit of what we can do. It's not 3-component data, it's just pressure. And it's not from the ocean floor, it's through conversion and some interaction. And there is that noise that I talk about, but it's after a while, it is basically the cost per P wave is negligible compared to an ocean bottom experiment. And so that's the trade-off that you're doing. We have 19 undeployed. That we had a Chinese partner who kept buying, and he wants to, help the global science. That's John Chen from SUSTEC, and so he's our main instrument pool owner now. And we want to get as many as possible. So my number is 300, but you're gonna have to buy them. So yeah, that's our plan.
How loud is the noise environment in the ocean versus the seismometer that's deployed on that?
Yeah, so in the 2022 paper of Joel Simon et al., we compare an island station, one of those high quality island installations that our community puts out, to a MERMAID, to a low quality raspberry shake station that also existed on some of the Polynesian islands. And on a noisy, stormy day, an island station is not very good. On a good day, a MERMAID is very good. And so we are sort of, and the raspberry is sort of in between. It's not, so we have numbers of detectability and, all sorts of reliability worked out, because that's exactly the question that of course we want to know. Compared to $35,000 plus, deployment, would we be better installing another island station? And my answer is no, because an island station is very expensive. It's not foolproof. It still gets very noisy. It also gets direct microseisms from the waves hitting it. And when it goes down in, you name it, some island where there's 3 people that live there, and there is a pandemic, then for 2 years they don't get serviced. And that's some of the situations that we have in our global seismic network, that some of these remote islands used to be reliable, but no longer are. And then that's what the community has to trade off. Where to put long-term stations, my view is let's keep doing that. I support it, I'm part of it. But in the meantime, we need to seed the ocean with low-cost instrumentation like this, which, while not perfect, gives us a ton of data. Nobody has ever written a paper from data from a land station that was out of commission for 2 years. So, but yeah, the best ones are better than ours, but it's not always the case. And the details are in the paper.
What's the lifespan of the current generation? So like you deploy it and you don't intend to retrieve it. It's got onboard batteries, but I didn't notice any like solar panels or anything like that. So like, what's its lifespan?
So it's 250 surfacings and the attendant, satellite communications. When we request hours on end for Hunga-Tonga, we're eating into that budget, which is why I initially was reluctant, but now I'm going for it. And I'm glad I did it. And that was because the instruments were also, they had already returned a lot of other science data. That's on lithium batteries, okay? There is a solution out there, commercial, just now, where you can add a sort of a battery to it that actually is a thermochemical electric conversion that will mine the gradient of the ocean's heat as it invariably needs to go up and down. There's a company called C-Track in San Diego that makes that, and they have just literally shown us a device that is in principle able to generate clean energy forever. We played with them, asked them, at the time they weren't quite ready, and the instrument would have been twice as big and twice as expensive. But I think that's definitely coming for next generation. And then there's a question, what else do you want to add? The next instrument we have coming has a conductivity temperature depth sensor also on it, so it can be like Argo for global climate and so on. That's going to eat into the budget. French colleagues in GeoAzur in Nice are thinking about actually having a bioacoustics package, which is a high frequency hydrophone to listen to whales, but then there needs to be trade-offs made. But the volume of battery at the current density of lithium batteries with the 40 hertz sampling, always on, always listening, always discriminating, and sending about 12 minutes of data every 5 days. You can do that about 250 times, which is about 5 years, given how many days there are in a week. And so far, we're on 4.5 for some of them. So that's the budget. It's also longer than all sorts of other instruments can do.
Thank you.
Yeah.
Would there be any advantage to dropping it all the way to the seafloor so that you can actually get coupling directly with the seafloor?
Yeah.
Or is it better for it to float anywhere?
It's not better for it to float. It's easier for it to float. And so we have another generation that I think is definitely coming now that we call the MERMAID lander, which will just go sit somewhere for a while and then still come up. There, the advantage is you can do regional events or landslides or something of local interest and you're not floating away. If you look at our array now, right, the whole point of getting the coverage that we were lacking in the world's ocean is because we are moving. That is, the motion of the array, this is our website, is a design feature. So this is today's array, right? And so, you look at instruments that have been there for a while, not that one actually, you know, these are 4 years of the life of this instrument. It's been in a lot of different places. And so I'll just go back to the all. So you don't see where they all have been unless I show you again one of those snake notes. But the fact that it's been all over has an evolving random aperture of an array that gets wider and more interesting. And so Polynesia that we really want is still here. So compared to Galapagos, where we sort of did a 300-degree turn, that wasn't really it. And so here we're just, it's getting better by the day. And so the motion helps, but it's not coupled to the ground. But we have developed a landing package. This is the group in France. And so we're hoping that that will get some traction. Anyway, you shall buy one. Highly recommend. Yeah.
Just curious about the algorithm used to get the data.
Yeah.
Like, are you using when there's an earthquake of a certain size around the globe?
Yeah. So we put the data through a digital STA, LTA, short-term, long-term average for what every instrument has. That gives us an interval of potential interest. Then we put it through a discrete wavelet transform, which breaks it down into coefficients that additively and completely orthogonally code for the entire signal without any loss. Then we put the distributions of coefficients through a historical data set. This went offline, that maps the distribution of those coefficients in the time frequency domain to the likely signatures of events, P waves, teleseismic, whale, you know, sort of thing, but it's a time frequency or rather time scale detection. And then we transmit literally wavelet coefficients. And so you can read some of it in this paper here. This is you know, some of the analysis that goes on board from the time domain record on the left. We never make the spectrogram on board because that's redundant and costly and unnecessary, but I do this here. That's the wavelet decomposition. And so that gives an almost unique barcode for high, low, you know, intermediate events. This is a spectral density, which we don't use, but so it's on the basis of this barcode and the statistics of it. And we currently call it a Sukovich algorithm after postdoc Alexei Sukovich, who used this principle of the breakdown combined with the statistical analysis of patterns to give us good enough recognition. And people always say you could do all sorts of different things, and I agree, but this is the one that's programmed on the machine right now. We can adjust certain coefficients of it, but we can't adjust the whole firmware of it, nor do we wish to because it's working very well. And then the wavelet transform breakdown is actually really good because we are not sending time domain samples anymore, but we're sending coefficients. And we're actually only sending half of the coefficients, which gives us an immediate denoising of it. But if you want all of them, you just send the number 5 to the instrument, then you get more of it. So we play a lot. That was actually most of the work to develop the signal processing, because while I had that one earthquake, I had nothing to do but look at other random events. And so we looked at that in detail. Yeah.
All right. So please hang out and ask more questions, but for now, let's end here and thank Frederik for a great talk.
Off the record.
You are.
That battery, I knew it was 5 o'clock.
Sorry about that.
No, that's perfect.
But that's, I don't think I've ever seen that happen before.
And batteries on the end.